So here we are going to see a problem, just what we are with numericals, what we have seen in the last video, that is how do you do for a simply supported beam the function of UDL, that is the function of reaction, shear force and bending moment diagram we have already seen, and how to proceed with it when you have numericals. Now just see, this is a problem in which you have a simply supported beam which is supported at A and B, and it have loads at these points. Let me note the points as D, C, E, F, G. That is, here you have D, then here you have E point, then you have F point and G. That is just the load points I have notated like this. And you have at D you have a 40 kilonewton load, then you have a UDL of 4 meter span, then you have 60 kilonewton load, then you have 80 kilonewton load. Okay, full span is 14 meters. Clear? Now using influence line diagram, we are supposed to determine the shear force at section C and also the bending moment at section C. Clear? Now just by starting to do this problem, just draw down the problem. What you need to know is, here your section is at C, right? From before we have studied that the distance of section is marked as Z. So you have Z as 4 meter. Clear? Then your other notation is L as 14 meter. Now what you need to recollect is, whatever you have studied for the simply supported beam, when when a point load passes over a section C, your shear force diagram, the ILD, the ILD for shear force, you have obtained it as like this, right? What I'm drawing now, we have studied it. And this portion, that is from A to C, the function is x by L. And C to B, the function is L minus x by L. Clear? So this is the equation. So surely we should know and we should remember all these equations, then only we can proceed with the problem. So you have the two equations for shear force. Now what we need to do is, as per the given figure, see this figure over here, as per the given figure, they have drawn the ILD for shear force at section C and they have marked the ordinates. How we'll calculate these ordinates? By substituting in this function, right? Now under each load, this 40 kilonewton comes under between A and C. So you should use the function x by L. And what is x? 2. And what is L? 14. So it is minus x by L. That is, from A to C you have the shear force value or the function as minus x by L, right? So your ordinate, you'll get it as 1 by 7. And at section C also you can calculate, and it is 4 by Z value is 4 and the total value is 14. There also you can calculate it, ordinate. So first, in this influence line diagram for shear force at section C, you need to calculate all the ordinates. Okay. Now using this function, check whether you are getting this ordinates as per this figure 5.11b. Clear? Now we just see our beam. We have point loads at D, F and G. So to calculate shear force, what you need to do is take this load 40 multiplied by 1 by 7. Okay. As it is negative, you should take minus 40 into 1 by 7. Now consider next point load. Next point load is 60, right? So under 60 you have, what is the ordinate? Under 60 you have the ordinate as 3 by 7. So 60 into 3 by 7. And next concentrated load is 80. 80 into 2 by 7. Clear? So, and all these with the respective signs, okay? So shear force at section C will be minus 40 into 1 by 7. Okay. Then the other point load is plus 60 into 3 by 7 plus 80 into 2 by 7. Clear? Now you can see that our beam also carries a UDL of 10 kilonewton per meter. So for the UDL, just see this shaded area. In the influence line diagram for UDL, you should take the load multiplied by the area which is under the influence line diagram. That is why it is shaded over here. So you will get it as minus 10 into 1. You should use the equation for trapezium, area of trapezium, 1 by 7 plus 2 by 7. Okay. And you have the other positive portion, and this multiplied by 2, then plus the positive portion also, that is 10 into 1 by 2 into 5 by 7 plus 4 by 7 into 2. Clear? Okay. Now you get the answer for shear force. The answer you will get it as 51.43 kilonewton. Just check it out whether you are getting the correct answer. Again, I am repeating, you should have the influence line diagram with you, and you should know the function also. Now, after knowing the function, draw the influence line diagram, and what you need to do is you just mark the ordinates. Okay, ordinates with the respective function. Write the ordinate value. Concentrated load multiplied by the ordinate, and UDL multiplied by the respective area. Okay, so you'll get the shear force calculated. Now we move on to determine the bending moment at the section C. Now to determine bending moment at section C, what you should know? You should know the equation for bending moment of a simply supported beam. Right? For bending moment, I have told you that up to section C, it was X by L into L minus Z. This is applicable on the left hand side of the section of the bending moment. Now coming into the right hand side, what you will use? L minus X by L minus X by L into Z. Okay. Now X is what? That varying value. And what is Z? The fixed value 4 always. Right. So for this bending moment over in this region, you write X by L into L minus Z function, and for this region it is L minus X by L into Z. Right hand side of the section and left hand side of the section. Now in the same way, what you should do, you should determine the ordinate values, and for concentrated load multiplied by ordinate value, and for UDL the area under it. Okay, see here they have given the ordinate values and also calculated, and you're getting the answer as 345.71 kilonewton meter. Okay, now this is one of the greatest application of influence line diagram also, because you know that to determine shear at a section you need to determine reactions and all, and you have to proceed. Now here that and all is not required, just go along with the ILD ordinates, multiply it or determine the area and get the answer. Okay, try working it out.